Hello and welcome to our webinar, Finding Leaks and Other Topics with Gary Nelson. My name is Bill Graber. I'm the marketing guy at TEC. And I'm just going to briefly introduce you to who we are, and then I'll hand it off to Gary. The TEC, or the Energy Conservatory, started 40 years ago by Gary Nelson. And at that time, he set the mission for the company, which was to develop air measurement tools and processes to help the industry deliver improved built environments, meaning that they were healthier, more comfortable, more energy efficient, and more durable. And so many of you know us from the products that we make, like the Minneapolis blower door and Minneapolis duct blaster, the associated gauges like the DG700, DG1000, and the new DG8. We also make air measurement tools for the HVAC industry, and these are things like the True Flow Grid and the exhaust fan flow meter. And we have a new product called the Digital True Flow coming out this month that is shown here on the slide. Overall, part of what drives us is that no matter which of these measurements you're making, over time we want to continue to make it easier to do it right. So here's today's agenda. And with that, I'm going to hand it off to Gary to take us through it.
Okay, this is Gary here to tell you a little bit about what I've been up to lately. People, when I run into them, ask me how I like retirement, and I am not at all retired. I am still working full-time, and I'm here to show you what I've been up to. And the main topic probably is a fog puffer that I've been working on for the last several years. Some of you have seen prototypes probably at conferences in the past. But I'm also working on some projects to improve the accuracy of the blower door when measuring air tightness, including wind effects and stack effect in big buildings. So we'll talk about those things. But we're going to start by doing a little background, a little history, and the importance of finding and fixing air leaks. Where when you're fixing leaks, the goal is to get the right person to put the caulk in the cracks and to do it properly so things don't leak. And I think there's three main things that can help you with that. Probably the most important is knowing something about how houses are built, and of course particularly the house that you're working on. But also we'll talk about using a blower door and an infrared camera together, and then the use of smoke and fog of various types. So first, knowing about how the house is built, the important thing is probably just about everybody here today is aware of that wood frame buildings have complicated leakage paths, and where interior walls and floors intersect the exterior walls or the ceiling causes air leakage paths where all the connections are. So for example, next I'm going to talk a little bit about how using a blower door with an infrared camera together is important. So imagine in this house we set up a blower door and we depressurize the house, and there happens to be a connection here where the attic above the porch or sun space is connected to this exterior wall, and what happens is air comes in from the attic into this wall, and it might find a connection into the ceiling cavity between the first and second floor of the house. And if we're down here in this room and looking up with an infrared camera, after a couple of minutes we see that the ceiling is getting cold. This is a technique that was developed by some researchers at Princeton. These two guys, Ken Gadsby and Gautam Dutt, were two of them that came up with this idea to use an infrared camera combined with a way to pressurize or depressurize the house So in the early 80s, I was getting interested in energy use in buildings and starting to do energy audits, early energy audits, and help to develop energy audits. And I really needed an infrared camera to learn from. In going out to houses with a blower door and infrared camera, I could figure out where all of the leakage paths were and so on. And Bill Graber dug up some old video that we used to uh, distribute, showing me out at a story-and-a-half house with an infrared camera, the same infrared camera that I'm shown with here. So we'll next show that short little video clip.
Usually what we do with the infrared scanner is to take two looks around the house. First one without the blower door running, and when we do this we're just making a note in our mind where we see unusual cold areas or unusual warm areas. We scan all of the exterior envelope of the building, including connections between interior walls and the ceiling of an attic space, between the interior walls and the exterior walls, and any place where we suspect there could be problems in the house. And we just make this mental note of any unusual areas that we see. Then we go around the house a second time after the blower door has been running for 5 minutes or so. And now any places there are air leakage paths, these areas will get cold because assuming that we're doing the scan when it's colder outside than it is inside, the areas where there are air leakage paths will get cold from the cold air that's being drawn into the house with the blower door running into the problem areas. In fact, we saw earlier where we sealed ductwork where it went underneath the knee wall, and what we found with our infrared scan is that we probably have missed some little bit of leakage in that ductwork where it goes underneath the knee wall. So we'll go up there with the blower door running later and check for that.
So back in 1983, even though this equipment was expensive and seemed exotic, I was pretty convinced at the time that anybody that is doing serious diagnostic work in buildings not only needs a blower door, but they also need an infrared camera. Now here's a picture of my most recent infrared camera made by FLIR, which plugs into my iPhone, and when I take a picture, of course, it's in color. And look at the cost. It's $400 for this, and this is the top of the line FLIR 1 Pro. And to compare that with the camera that I got in 1982, a friend of mine and I went together and bought a used AGA 720 for what would be about $60,000 today in 2021 dollars. So if I thought it was worth getting then for $60,000, certainly it's worth 400, and nobody should be out working on houses doing diagnostics, I don't think, without having an infrared camera. So next we're going to just quick go through what are the various techniques that are used for finding leaks in buildings, and this is a list that comes out of the ASTM E1186 standard, which is a standard for finding leaks in buildings. First of all, a blower door and infrared camera, and then we'll talk quite a bit about smoke and fog, various types of smoke and fog generators that are covered in E1186. But Henri Fennell, who was a member of that committee, came up with a much more detailed procedure, and I think it's much more useful for somebody that's thinking about doing this, especially in commercial buildings. And we'll post that on our website at this location so that you can look that up. And then there are some tracer gas measurements where you inject a gas in one part of the building and then pressurize and then sense with a sensor if that gas is leaking into other parts of the building, and it gives you an idea where the leakage paths are. Also, there are techniques where you put a sound generator inside the building, for example, and then have special microphones on the outside of the building that can detect that sound. And then you can also use an anemometer for detecting leaks. And the way this works, if you have a hot wire anemometer and you know that there's a potential leakage site, you hold the hot wire anemometer in where you think that there's an airstream, and if there is, it'll register the velocity of the air coming in. And this last technique that I have listed here, the zonal pressure diagnostics, isn't in E1186, but probably should be. And the way this works, you pressurize part of the building and then you measure in another part of the building or an attached garage or crawl space to see if there are leaks between the main part of the building and that zone that you're measuring in. You'll see the pressure change in that zone, and there's quite a detailed procedure for doing that I'm also not going to talk about in any more than this today. Just mentioning it. So we're now going to talk about smoke and fog, and we're going to start out talking with more high volume fog or smoke generators, particularly theatrical fog generators. And one thing that this is really pretty useful for is demonstrating leaks to architects and builders who, when you tell them that their building is leaky and you tell them it has 6,000 CFM 50, they don't know what that means. But when they see the leak pouring out of the cracks or pouring out of the windows or wherever, it sort of convinces them that this is really something that shouldn't be. It's also good at following and figuring out large complicated leakage paths and for use finding leaks in duct systems. And this is covered in E1186, but in much more detail in this procedure that Henri Fenel wrote. So Henri Fenel he divided these techniques into really three methods. In one method, you pressurize the building or a whole room with a blower door or another fan, and then you fill the whole building or the whole room with fog, and then you go outside and you see where the fog comes blowing out, up in the attic or sometimes in the soffits or wherever the leak goes. And then method two, instead of filling the whole room or the whole building, you build a tent, often out of sheets of polyethylene and tape, so that you isolate a part of the building that you want to test. In this case, a window. You might tape poly around a window and then blow air from a fan in behind the plastic while you also inject fog behind the plastic, and then you go outside and see where the theatrical fog comes streaming outside. And the last technique, the third method that Henri talks about, is where you use a fog generator to kind of lay down a blanket or to wash an area with as much thick fog as you can, and then you go on the other side, and like the other two techniques, you look for where the fog comes blowing out through the leak. So here is one of the theatrical fog generators. This happens to be Terry Brennan's, Terry has done lots of diagnostic work on complicated building failures in commercial buildings, typically, houses also. So these theatrical fog generators, this one's made by a company called Roscoe that's still in business and still makes these larger fog generators. These fog generators usually are just designed to dump smoke into the room that they're in. But in this case, Terry wants to have that smoke go into a flexible hose so he can direct the smoke to wherever he wants it to go. And he has attached an inline duct fan to the outlet of his fog generator to make a device that's creating pressurized fog that he can direct to wherever he wants it. In this case, a worker has a piece of PVC pipe connected to the end of that flexible pipe, and he's trying to wash this joint between the roof and the exterior wall of a commercial building where leakage is suspected, and then somebody on the outside is watching to see if they can see where the leaks and the fog is pouring out on the outside of the building. There's just another shot of that showing that this is a lot of fog. This device will generate thousands and thousands of cubic feet of fog per minute, and allows you to fill up some pretty big spaces pretty quickly. Here the same technique was used, but now they're laying this blanket of fog down at the bottom of a wall on the other side of this wall to see if the drywall is sealed to the bottom track of this metal stud wall, and of course you can see here that it's not sealed very well. And this is where somebody that wonders, does this really matter? When they see the fog, it kind of makes believers of people. This is another use of theatrical fog where Mike Uniac, a friend of mine, is injecting the theatrical fog into one of our duct blaster fans that's pressurizing a residential duct system. And then you go on the outside of that duct system and you see where the fog is pouring out. But in this case, he's shooting the fog right at the motor of the fan, and that motor is a brush type motor, and it now gets gunked up with this fog fluid, and then dirt sticks to it, and before long the motor will need to be repaired, and so this is a no-no to do it like this. We tell people that if you do this, ideally use a different kind of a fan. Use a inline duct fan or some other kind of fan. But if you do use the duct blaster fan, take all the rings off and try to inject the fan way out at the edge of the fan so that all of the smoke goes just through, hits the fan blades and does not get into the motor. And in most cases that works fine and doesn't seem to damage the fan. But we've seen lots of fans come back where people have injected the fog into the motor and it's destroyed the motor over time. So next we're going to talk about more low volume smoke. So we're now talking about smoke pencils, smoke matches, fog puffers, and so on. And this is particularly a good technique for somebody that's actually doing air sealing work to be able to see and prove to yourself that you actually fixed the leak. We're going to show a little video. Even though there's insulation and a lot of stuff in the way so that you can't see very well, when you squirt smoke you can see the fog very easily going into where the leaks are.
With the house depressurized to about 30 pascals, we can see lots of leaks.
Now, oh boy, we find a duct, a supply duct, that's leaking. And this is relatively more important than the other ones because we're using heated air. And it is tin, but we sure don't want to skip any supply side leaks. This was leaking a lot. And now the only air movement is over to the next. We got a big one here. So, got it.
Okay, so in that video, I thought the most interesting thing was Jim thought he had sealed the leak, but then he checked with smoke and he found that, oh, the next joist space over now became the leak instead of the leak that he sealed, and he didn't stop sealing until he stopped there from being smoke going into all of the leaks. And I think that's something that anybody doing a lot of air sealing, especially in existing houses where things are dirty and there's insulation in the way, it really helps you see what you're doing. So next we're going to just talk about some of the products, and I'm going to show some of these in a couple of minutes. Back in the old days, people, and maybe still do, use incense sticks, cigarettes. There are things that look like matches, but when you light them, they just make a big puff of smoke. I don't have any of that to show you. And then there's some really fine white powder that you can spray out of a bottle. And then there are several different kinds of chemical smoke. My favorite is titanium tetrachloride, which is used in squeeze bottles and glass. There's a glass smoke gun that I'm going to show you, and then there are smoke sticks and other uses of other chemical smoke. This place, Region HVAC, if you go to their website, you'll find that they have a lot of these different devices, and they're actually fairly inexpensive and are useful. So next I'm going to talk about, we're starting to get into the product that I've been working on, which is based on a vape pen or a vapor pen. And I want to, before we get into that, talk a little bit about how a vape pen works. Of course, here normally somebody would be drawing smoke out of the end of the vape pen, and that causes the air to be drawn into the vape pen at two different locations. Most of the makeup air usually comes in at the threaded connector between the cartridge, which contains the fluid and also contains the heater, and the battery section, which contains the battery, of course, but it also contains a little circuit board on the end here that has a pressure switch and an LED light and some other circuitry that causes that light to flash when the battery level is down and it needs to be recharged. That stuff is all located on this end. So when you draw on the e-cigarette or the vape pen down here, there's a hole that causes a suction to be transmitted into the battery section, which causes air to come in here, and then that triggers the pressure switch, which turns the LED light on and the heater on. So here you can see this is the cartridge, and this one is clear, and you can put liquid fog fluid in that cartridge. The actual heater is right in this area, and you probably can't see it, but there are some little holes drilled, and when you look in those holes you can see a white substance. That's either a ceramic device or a cotton wick that wicks the fluid into this area, and then there's an electric resistance coil in there that heats the wick or the ceramic up to create the fog. And it's actually not burning the liquid, it's just evaporating the liquid. And once this vapor, now this is a gas that is formed in the heater, that gets drawn and picked up by the flow of air that's being sucked through the device, and that air comes through this little tube, and then it's connected with an O-ring to the mouthpiece, and then normally would get sucked into your mouth. So the main ingredients of the fluid that's used both in theatrical fog generators and vape pens, it's the same stuff. It's normally a mixture of propylene glycol and vegetable glycerin. And a lot of people say, oh, well, these are not dangerous at all because they are both used as food additives and in cosmetics. But of course, if these are in a food additive or in a cosmetic, they're not vaporized into tiny, tiny particles that breathe deep into your lungs. So I'm not saying that just because this is used as a food additive that it's okay. And I think that the little bit that you probably breathe when you're just breathing the bit when you're using them is probably not a big deal, but I wouldn't intentionally try to breathe in a lot of this stuff. So I had the idea maybe 3 years ago that isn't there some way that we could use a e-cigarette to make a fog puffer, and I've been tinkering with this for several years. Bill Graeber thinks I'm the Thomas Edison of vape pens or of fog generators. I don't know about that, but I have tried. I have, you know, Edison was big about trial and error, and there is no such thing as a mistake. You do something and it doesn't work, and you learn from that, and then you try something else. And so on this top picture, I first was just using little squeeze bulbs that I was amazed to find at Amazon. You can buy about 30 different manufacturers of squeeze bulbs of all different sizes, and this is my current squeeze bulb connection. But then after a while I realized that, oh, a turkey baster really is a better thing to start with. So this is my turkey baster collection, and I've probably got 30 different brands of turkey basters now. I bought at least one of every one that I could find on Amazon, and also I have quite a collection of various vape devices, vape pens, and these bigger things for cloud chasing. People that are into seeing how much fog they can breathe into their lungs and how big a cloud of smoke they can make. They buy these big things. So here's my test kitchen. In this case, I'm testing different check valves that I'll talk about later. So I will squeeze this one 10 long squeezes, and then I'll set that one down and then squeeze this one 10 long squeezes, and then this one, and so on. And then after I'm done, I go back to the first one and do 10 more and 10 more. And usually in a session I'll get at least 100 squeezes per fogger, and generally it turns out that a fill of the fog fluid will last about 150 to 175 full big puffs, and I'll show you what I mean by a big puff in a little bit. And I think that that's as much as most people would ever use in a day. And then a battery charge typically lasts about 2 or 3 refills of the fog fluid. So here is what the fogger looks like, and we'll just go, and I'm going to give you a little demonstration and show you how it works. So this is the final. I don't know if there'll ever be a final, but this is the current prototype, and I've tested this up to 1,500 or 2,000 puffs, and it seems to be quite durable. And so this one has a check valve here, so that when you, and here I'll give you a nice big puff. It really makes, you can squeeze just really lightly and get a real nice narrow stream, or you can get a pretty nice big puff. It's really, the rubber bulb is soft so that you really have good control of the size of a puff you get. Works nice. So at the end of a puff, it's the same thing with that. If I didn't have this check valve here, now all of the makeup air has to come back through the e-cigarette, and that will eventually cause the pressure switch to fail. So I also have probably a sample of 40 different brands of check valves for aquariums and for gas lines on cars, for all different kinds of check valves, and found the ones that would let almost, this opens at a really low pressure, but not zero, because you want it to be closed when you give it just a little squeeze. But when you let up, you want as much air as possible to come through here rather than through here. And this, I still haven't had that many failures to know for sure, but this appears to have solved the problem of the pressure switch failure. I think eventually what is going to fail on these devices probably will be the pressure switch. So I'll show you a little bit more about this. You can see now that when I squeeze, the light on the end of the e-cigarette lights up. And when the battery becomes near its end, needing to be recharged, that light will start flashing, telling you that it's time to recharge the battery. So I want to show you how to change the battery, charge the battery, and refill the cartridge. And we'll start by just taking the stopper off. This battery and the stopper should slide up and down on the battery and the cartridge. If it's sticky, you can just put a little bit of the fog fluid on there or a little Vaseline or something. That works fine. So once you retract the stopper a little ways, you can see the connector between the battery and the cartridge, and you unscrew this, and then this is the charger that screws in, and then you plug it into any USB charging device. So when you put this back together, I recommend pushing the stopper all the way up past the seam between the battery and the cartridge, so that it's just at the very bottom of where the glass part starts. That way you seal this place where air would normally be able to go in or out, depending on whether you're pressurizing or depressurizing. And that forces all of the air to go in through the end. And then in order to fill, you can see that this cartridge is mostly full. The liquid level goes up here. I don't like to fill them any higher than the top of the glass. I always like to see just a little bit of airspace at the top of the fluid. But in order to fill it, the mouthpiece unscrewed. Whoops, I'm taking the battery off. I have to grab here. The mouthpiece unscrews, and then you take your bottle of propylene glycol and just stick the needle down in between the center tube and the outside edge, and you just squeeze until you get the fluid up all the way just about to the bottom of the stainless steel ring here. I've been using 100% propylene glycol. Most people use mixtures. I'm using 100% propylene glycol because it's thinner than the vegetable glycerin, and I think it's going to get wicked into the wick or the ceramic element in here and bring it into the heater faster, which will mean it'll recover. And I'll demonstrate this. If you squirt several big squirts of smoke, the smoke density goes down, and it recovers faster, I think, when you use the thinner material because it wicks in faster. But that's something where, boy, if people did some experimenting with different mixtures of the propylene glycol and the vegetable glycerin, that would be great. The kit that we're going to be distributing, though, will come with just 100% propylene glycol. So I'm going to screw the mouthpiece back on. And it turned out, we've been using these little tubing connectors for years, and it turns out this is slightly tapered, and this is just a perfect friction fit. And putting that tube, this small connector in here, gives a lot skinnier and nicer, smoother flow coming out. So this improves the flow and the look of the smoke. So there, it's back to normal. So now if I make a big couple of squeezes, you may notice that eventually, probably on like this squeeze, it still looks pretty good, but eventually the smoke gets thinner, and when it does, then if you turn the e-cigarette up so that the connector is facing up, so that the fluid can get absorbed into the wick or into that ceramic element. After a couple of minutes, you'll get good thick smoke again. That's just, you'll learn. And there is a little bit of part-to-part variation. Some of them seem to wick faster than others. Each of the kits will also come with this little, it's a bar straw connected to a little piece of silicone rubber that just fits on the end to give you a little extension that also gives you a very nice thin stream. And we're going to send 2 of these out so you can put a second one on, and now you get, pretty long extension. So in a house with a 9 or maybe even a 10-foot ceiling, you should be able to reach recessed lights and heating and air conditioning grills and so on pretty easily with that. So a couple of weeks ago, I sent several of these out to people that I knew get out in the field a lot. And one of the people I sent a couple to was Anthony Cox in Virginia. And he, like 2 days, got back to me and said, "Oh, I have an idea of how you might improve that." And he said he thought it needed a flashlight. And I told him, when I was working on this one, I actually had a little flashlight and I used it, and it worked pretty good. But then I thought, well, most people when they're out inspecting a house probably have a headlamp on, and so you don't need the flashlight. And Anthony said, "Oh, no. He thought the flashlight would be good." So I haven't figured out yet the best way to attach this, but I'm just going to do a little demo, and I don't know where's the best way to show this. I'll do it here because I have my dark shirt on and you can maybe see. But then if we put the flashlight on, and it turns out the flashlight, I guess I have to put it this way. This is a flashlight that Anthony actually had picked out because it's an inspector's flashlight. It makes a really narrow, bright beam. And if you get it aimed right, it's just right there. And you can actually test it. If you look at a wall, you can see, does the smoke hit the circle? And it does. So I need to figure out a better connector, probably a connector that attaches here that you just push it on or something. But we'll figure out a connector. And if people want to play with other flashlights and get back to me, that would be great.
So now I want to talk about a little bit about the kit that we've put together and are going to have for sale starting probably next week or the end of this week. So it consists of the fog puffer that you just saw, everything that you saw, and there is an extra battery in this box. And actually, when we ship this to you, this battery will also be in a box. That makes shipping safer. There's a little bag that it's in, a plastic insulating bag, and then the bag goes in a box. And then you'll also get a spare cartridge, so that if that fails. I have so far, out of all of the testing that I've done, I've had about 4 batteries fail, and I think it's always been the pressure switch, although I have not taken them all apart to verify that. And I've had no cartridges with the heaters fail, which surprised me. I thought that would be the main the main failure. In addition to that, you'll get the 2 little extensions, charger, and then I think it's a 4-ounce bottle of propylene glycol and the filler bottle. So you fill this bottle from this bottle. The end of this is too big to be able to get in here well without making a mess. So we're going to initially sell this entire kit for $59. There will be spare batteries and spare cartridges available, and other parts can certainly be available. And we're going to have a drawing and draw for 25 of the people that are attending this webinar to get a free kit, because we want people to try this out and give us feedback and tell us what's wrong and how can we make it better. And we will then be taking those ideas and incorporating them in a final design, and we will let you know by email. And oh yeah, we had on the bottom of one of these the things that we. Oh, I bet that's in the next slide. Oh, okay. Yeah, sorry. So a couple of helpful ideas that I'm looking for are, one, how to carry this. I'm thinking maybe some kind of a strap that maybe mounts, that goes around the end of the bulb, or between the check valve and the bulb, that you can put over your shoulder. Anthony Cox suggested a little bag that was big enough to put everything in and clear, so that you could have spare parts. Maybe you actually assemble two complete e-cigarettes that are fully charged and fully loaded, so that if anything goes wrong, or you run out of either the charge or the fill, you just take this one out and swap that one in. Or you could put the bottle of fluid in the bag with you. And then the other thing that would be nice would be a name, a catchy name. I don't remember who it was. Somebody came up with the idea duck blaster, and that's stuck, and that's our current duck tester, is a duck blaster. So is this the turkey blaster, or the turkey fogger, or the fog baster, or what? Those are some names that I've called it from time to time, but I don't think we have the right name yet. So if anybody has a clever name, we'll give you 2 free kits. And then this is, of all of the commercially available foggers, this is the one that I really like the best. It's available from this company called VossenTech.com, and at their website, and it has a remote control. The remote control and this adapter, so that you can connect a hose to it, are options. But with those options, this is $174. It produces a lot bigger volume of smoke. I don't know how often that will be useful. Of course, it's a rechargeable battery, and it's operated by there's a small fan instead of a squeeze bulb to make the smoke, get the air to flow through the device. But I like this a lot, and at least one customer of ours has told me that he's been using this, and he actually says it makes enough smoke to do a leakage test on a duct system by pressurizing the duct system with smoke. I don't know. It seems like that's a little bit too little for that, but maybe it works fine. This is largely made for people that are making movies or photographs, that want to add a little smoke to the background and make things look cool. And so I think the biggest market for this is photographers and video artists. So next I want to go to talk about a couple of the things that we've been working on to improve the accuracy. And first we're going to talk a little bit about reducing the effects of pressure fluctuations due to the wind. And we last summer did a whole webinar on wind, and I'm not going to go over all of that, so you might want to look at that. But since that webinar, I've been doing some more measurements and more puttering and thinking. And one thing that I've noticed in the last couple of years going to international conferences is that the Europeans always recommend that you put a T on the end of the tube that goes to sense the outdoor pressure when you're measuring the pressure difference between inside and outside. And I've questioned that, so I did some measurements, and I found out that indeed that is a good idea. It sometimes helps reduce fluctuating pressures, Sometimes it doesn't, but it doesn't seem to ever do any harm. It sometimes helps. And I took that idea and thought, is there some way to combine that with a device that would at the same time keep the end of your tube from getting wet in a rain, or if there's some small puddles around. So I came up with an idea for that. So first of all, here's some of the comparison measurements that I did at my house. So I'm sensing the outdoor pressure on both of these tubes. One that has just the little T that comes with your blower door accessory parts, and the other one does not have a T. And this is just sitting out in the middle of my patio on the east side of my house. And on a windy day, actually on several windy days, I use TEC Log to data log the pressure difference between inside and outside. And often at this location, the T helped quite a bit. You get fewer fluctuations, less noise. It tends to damp out some of the noise. So this is the thing I came up with. This is just a larger T, and I compared it against the smaller T, and they both worked equally well. But this larger T gets here you can see it a little bit better, where it's right up where the wall of my house meets the patio. There's a right angle fitting, press fit into this piece of PEX, and when you lay it like this so that that right angle fitting is up, the end of that fitting that's in the tube is high enough off of the bottom of the tube so that if it rains, water can actually flow through the tube, but it stays low enough so that it doesn't get into the end of the tube that's sensing the pressure. So this seems to work really well. I've had this out in the backyard and been spraying with my hose on it and gone through several big rains, and it seemed to work just fine. When I compared it against just a tube, so this is another tube that's sensing the outdoor pressure right next to this one, the T really did not help in this case. This is already somewhat out of the wind because it's where the ground meets the wall, which is where I've been telling people to place their outdoor hose for years, on the leeward side of the building. And it doesn't help with wind pressure fluctuations at this location, but it is going to keep the end of the hose out of the rain. And in this condition, it helps with both the wind and the rain. So we're going to start providing one of these T's with every blower door kit in the near future. And another bit about wind. So at the last 2 or 3 AIVC conferences, which are usually held in Europe, there's been quite a bit of research lately on wind pressure fluctuations and how you can improve your measurements in windy weather. And one of the main recommendations has been, when it's windy, take readings where you average over longer periods of time. So we've made a bunch of measurements. We found out that indeed that does help a lot, and we're now working on our software auto test. We're working on what we call the wind assistant, kind of like the tubing assistant, but this is a wind assistant that will prompt you when it detects that there's lots of wind pressure fluctuations. It will prompt you to make your measurements over a longer period of time and automate the whole thing. So there will be a webinar coming up on April 22nd with Colin Olson, our senior physicist, who has been doing more of that work. The last topic of the day is a little bit on, we're getting now kind of into the weeds on the stack effect in bigger buildings. Colin Olson and I, with the Energy Conservatory, just worked on a paper that was published in Energy in Buildings. We worked with Remy Carré from France, who's been doing research on all sorts of things related to buildings and ventilation rates. And actually, he was a PhD student with Mark Madera at University of California at Berkeley, and his PhD thesis was involved with the invention of an aerosol sealing device to seal ductwork called AeroSeal. And he did a lot of the theoretical physics work to try to figure out what size of particles do you need, what kind of airflow do you need, will this actually work or not? And I don't know if he's on some of the patents. He probably is. So anyway, he's the one that actually did the math, and Colin and I tried to keep him practical so that we figured out that if he couldn't explain this to us, we're never going to be able to explain it to anybody else. So we kept him trying to simplify things so that we could understand it, hopefully then that it would be more useful. And I think he's come up with some really important stuff. So this is called building airtightness measurement uncertainty due to a steady stack effect. And here we see a tall building with the pressures due to the stack effect. And the motivation for this is that when you're in a tall, there are standards that require that at the beginning of a test you measure, in Europe they call it the zero flow pressure, we call it the baseline pressure. But if the baseline pressure is above about 5 pascals, I believe, in this European standard, you're not allowed to say that you have a valid test. Well, it turns out a 20 or 30 story building, the temperature difference between inside and outside only can't be more than like 5 degrees, so it severely limits the weather in which you can test tall buildings. And nobody really proved that, or I don't think anybody really had much of an idea at all if 5 pascals was too low a pressure or too high a pressure or what to cause errors due to the stack effect. So the purpose of this study was to try to understand better how stack effect causes errors in blower door tests. And here we'll prove that we're into the weeds. I'm gonna try to explain the most important and maybe the simplest graph in the paper. So on this graph, along the x-axis, it says that this is the dimensionless induced pressure. What that means is that's actually the induced pressure. Like, say we're going to do a blower door test and test the air leakage at 50 pascals. 50 pascals is the induced pressure. But we make it dimensionless by dividing by what's called the total stack effect that you can calculate. It's just related to the height of the building and the temperature difference between inside and outside. So this is the induced pressure, but dimensionless, but made dimensionless by dividing by the stack effect. And then this on the y-axis is the absolute value of the maximum error that you could have due to the stack effect. And each of the colors are determined by what the flow exponent of the leaks are. In this study, so far we've assumed that all of the leaks have the same exponent. We are planning to work on an addition to this study to show that this would also be true for if you have multiple exponents. So one leak might have one exponent, one leak might have another one. And we strongly expect that the results of this study are still going to be true. So I'm just going to go through one quick example of what this would tell us. So I'm going to say we have a 3-story building on a day when it's 0 degrees outside, and the building is 30 feet tall, and we calculate that this would be a 15 pascal total stack pressure. And then we're going to test it. We want to induce a test pressure of 50 pascals. And that means 50 divided by 15 is 3.3. So on the x-axis we would be at 3.3. So we go up until we get to the line that, and we'll assume that an average typical exponent for a building is 0.65. So I'm going to go up to the line that's just starting to turn orange. In this part of the graph they're all so much together that you can't really see. Oh, I can go to the next slide and we're going to zoom in. So here's that induced pressure is 3.3 times the stack effect pressure. And then we can see that the maximum error would be something less than 3%. This would be 10%. Here we go up 3%, something like that. Maybe that's about, looks like about 2.5%. So even though you may measure the baseline pressure at the bottom of this building could easily be 10 pascals, and according to the ISO 9972 standard, you can't do a valid test on that day because the stack effect is too high. But this graph tells us the worst case error due to the stack effect is less than 3%. So why not? So we're hoping that this gets used by people writing standards and people developing. We certainly will use it in our software where we estimate what the plus or minus values are associated with, say, CFM50. You might get 1500 CFM50 plus or minus 100 or 50. This will allow us to better estimate what that plus or minus number is, and it'll, we hope, get used by people that are involved with standards writing to make it easier to do a test on a day when it's cold out and there's a lot of stack effect. So I guess that about wraps up this webinar, and this kind of points out that we're always here trying to make it easier to do things right.